it's quite important to think about what changes in time, right? What are we trying to describe, right? As chemical engineers, we're trying to describe the concentration of different variables. So what types of concentration are we talking about here? Where, of course, depending on the number of species, say oxygen and nitrogen for the sake of oxygen purification, it's binary mixture, right? So there's two components. So there's actually the number of components are important, right, when it comes to deciding these variables. But there's also two different phases, right? The the free gaseous phase and SR phase, which is the condensed phase, right? So there's always going to be two phases that we're going to model, and there's going to be different number of species. It's general up to however many number of species you want to consider. So we're interested in the gas phase concentration of those species as well as the SR phase concentration of those species. So how do we define those concentration variables, right? Where we start out by defining this N and N hat, right? N is the number of moles of the adsorbate in the gas phase, and N hat stands for the SR phase concentration. So with this definition, the amount, number of moles divided by volume, and in this case, the volume epsilon is actually, as shown here, it's the bed void fraction combined with the macropore. Remember that we consider micropore as SR phase, part of SR phase. So basically, by dividing the total number of gaseous molecules for ith species in nth CSTR, so notice this subscript, right? N means nth CSTR, and I means species number I. By dividing the amount or the number of moles of the species I in nth CSTR by the volume occupied by those gas molecules, we get concentration of gas phase. SR phase is the total amount of SR phase concentration of ith species in NCSTR divided by the, again, this is the density times volume, right? So it's defined per mass, right? This mass over volume times volume. And we can actually consider some of these individual gas species concentration as the total gas concentration and total SR phase concentration respectively. And of course, we're interested in the temperature dependence of the adsorption capacity, right? In general, the higher the temperature, the lesser amount of species will adsorb, right? Because of the thermal energy. It's important to consider temperature as a state variable, meaning the things changing with respect to time. And T and W is just corresponding to the external, the world temperature of a tank. So we model two temperature per tank or per CSTR. So those are actually pretty much it. So we can concatenate these concentration vectors for gas phase and SR phase as well as the two temperature variables into single x lowercase bolded phase vector, and xn represents all the states that belongs to the nth CSTR. And you can imagine however many number of CSTRs we're gonna stack up to model the packed bed. And the more CSTRs you stack up, the more accurate the profile, especially the sharp change in concentration, you'll have better resolution, right? Because you have a more fine, you can capture more fine, changes. However, the more you add these volumes, of course, the computational cost will increase. So depending on your application, you need to determine the right number of the CSTRs or the number of discretization points.